Good afternoon, everybody. This is Andrew Braham. Thank you for joining me for our Pavinar today. And today's topic will be stone matrix asphalt. Before we begin the technical content, if you cannot hear me talking now, please check your computer volume and/or your speakers. And if those are both in working order, you can go into the Illuminate software, go to the Tools bar, into Audio Setup Wizard, and then follow the instructions for help. If you have any questions during the Pavinar, I encourage you to raise your electronic hand, and that hand is listed or is located directly underneath the list of participants on the left side of your screen. And when I see a hand being raised, I will either pause then or pause at a convenient break, and then you can simply type your message into the chat box, which is located beneath the electronic hand. And if I know the hand is raised, then I can wait for the question to be typed in. After the presentation, a little later this week, professional development hours, or PDH hours, will be emailed to you, and those will be sent to the email address that you used while logging in to the Pavinar. I would like to thank the New Mexico DOT for requesting the topic stone matrix asphalt. I feel that these webinars are for the pavement community, so if you have any topics, please feel free to go through the website where you can submit them electronically. This is a brief outline of what we'll talk about today. First of all, we will give an overview of stone matrix asphalt and a brief history of it. After that, we will go into some of the design, which will include materials and mixture proportioning, and then some critical properties. SMA is asphalt concrete, or hot mix asphalt. A lot of the design, however, comes from the fact that it has a unique gradation, so we'll spend quite a bit of time talking about that. We'll also briefly discuss the production and construction, including some of the materials and equipment, and then the laydown and the compaction, just to kind of give an overview of that. And then I found a couple of good resources from Illinois, Wisconsin, and Virginia. So we'll just go over some real brief field examples. Nothing too big, but I'll also provide some electronic links so you can look into those further. So what is stone matrix asphalt, or SMA? You can see this is a picture of SMA from the side view, and it does consist of simply aggregate and asphalt cement, but the aggregate is gap graded, meaning that it's a very specific one-size aggregate gradation. And that causes the mix to be highly reliant on large stone-to-stone contact. So over the next couple slides, you'll see several examples of what I mean by the gap-graded effect and then the stone-to-stone contact, and how that's different than the more traditional hot mix asphalt or asphalt concrete. In terms of its use, SMA is often used as a surface course, so this is not something that is generally found in the lower layers of the asphalt pavement. It's usually found right on the surface. It is designed to be very durable and highly resistant to deformation, so you don't want to have any sort of, or you don't expect to have any sort of rutting occur when you use SMA. A very important note is you do need to have a high density screed during the construction. I'll talk about that more in the later production and construction section, but it's critical that you have that in order to achieve the proper compaction. You generally use very hard and cubical coarse aggregate. This type of aggregate encourages and promotes the stone-to-stone contact, which allows you to resist that rutting. And the aggregate is held together by what's called a mortar. So you have this hard cubical coarse aggregate that's held together by the mortar. And what the mortar is it's an asphalt mastic. And when you say asphalt mastic, you can be talking about a combination of the P200 fines, so the very, very fine material, and also the asphalt cement. When you mix that together, the asphalt cement becomes extremely stiff, and it's called asphalt mastic or mortar. Some of the advantages to using SMA is that you do have a relatively high resistance to rutting. You can have improved low temperature performance, especially in regards to cracking. You also have an improved macro texture. This can help with skid resistance, and also that macro texture allows a reduction of tire noise. And then finally, you do have some ease of compaction using static rollers. So again, when we go into the production and construction, we'll learn a little bit more about the rollers, but if you use the proper roller, the static roller, you do have some ease of compaction with this single roller. This is a very nice picture that I was able to find on pavementinteractive.org. You can see the link on the lower left. If you are not familiar with pavementinteractive.org, I highly encourage you to check that out. It's basically, I kind of call it like a Wikipedia for pavements. And I will put up a link here in a second. I kind of consider it a Wikipedia of pavements. You can search for anything, including both rigid and flexible concrete. And I put a link in the chat box on the left there. And it's free of charge, and it has, it's amazing. It almost can completely replace a textbook for an Introduction to Pavements course. So it's very comprehensive. But they had this very nice picture of stone matrix asphalt, or SMA, and you can see the coarse aggregate has the strong stone-to-stone content. Then you have what are called inactive particles. You obviously don't have only one and only one single size only of aggregates. That would be very hard to process. So there are some what are called inactive particles that are almost kind of floating in between the larger coarse aggregate. You have the asphalt binder, which is also called asphalt mastic in this case because of the P200. And then you also have some air voids in there. So going through those three steps, the structure of SMA really begins with that coarse aggregate stone-to-stone contact. And a lot of people call the aggregate structure an aggregate skeleton because that's how the load is transferred down into the pavement, just like bones transfer the load through a body in your skeleton. And this stone-to-stone contact reduces the rutting. The structure is held together by mortar, and the mortar is both the inactive particles, which are the smaller aggregates that do not participate in the stone-to-stone contact, and then also the asphalt binder, and that's usually a relatively high amount, around 6%, and that's also mixed with that P200, which gives you your asphalt mastic. And we'll go into more details on the mix design in further slides. And the resulting mix has a relatively high VMA, about 17%, but it does have lower air voids, either 4% or less than even, because most of the VMA is filled with the asphalt binder. And the reason, another benefit, not only holding together the aggregates, the asphalt binder is able to prevent drain down. So drain down is where, when you're making asphalt concrete, if the asphalt cement literally drains off of the aggregate and then starts going downward through the pavement structure or downward in the silo in the plant. And you really want to reduce drain down because you want to have a consistent mix with consistent amounts of aggregate and asphalt cement throughout the entire mix. And drain down actually has the asphalt cement going toward the bottom of the mix. So you want to reduce that. So those are just kind of a couple introductory high points to SMA, and we'll go into a lot more details about that. But before we do, I thought we would just give a little bit of a history of SMA. First, SMA was developed in the 1960s over in Germany, and it's been used extensively throughout Europe for the last 40 to 50 years. So this is by no means a new technology, but it does have, I think, less application in the United States versus over in Europe. In the 1980s, Canada had success on several projects, so they've continued to use it, but it really wasn't introduced into the United States until the 1990s. And that was after there was a scanning tour of Europe by state agencies, federal agencies, also I believe some contractors. They went over to Europe to see what Europe was doing to construct their roads, materials they were using, new technologies, and they witnessed some SMA projects. They liked what they saw, so they brought that technology and they brought that knowledge back with them, and it has since been introduced to the United States. So that is just a brief background. As I mentioned, we're going to go over, I went over a lot of details. We're going to go over those in even more detail in the next 3 sections. But if there are any questions at this point, I encourage you to raise your electronic hand, and I'll wait for you to type them in. With no questions, I will move on, and we're going to be talking about the design of SMA. So when you're looking at SMA, you have very similar base materials to traditional HMA, or asphalt concrete. You have your aggregates, you have your mineral filler, which is the P200, and you have your asphalt binder. But you also have something called a stabilizing additive. And those stabilizing additives are used in order to prevent even more drain down. If you can imagine in a typical dense graded mix, there's less opportunities for the asphalt cement to drain down through the mix, but with a very open mix, using that coarse aggregate with the stone-to-stone contact, there is a higher chance of drain down occurring. In order to combat that, we put stabilizing additives into the mixture. Also in the design of SMA, we're going to talk a little bit about the gradation, the very importance of the gradation, and then some of the volumetric properties as well. So this table is taken from AASHTO M325 stone matrix asphalt. And you can see for the aggregate properties, they divided it into the coarse aggregate and the fine aggregate portion. And you can see that there are several tests listed along with the AASHTO recommended limits. So for example, the LA abrasion, that you want to have very strong, very durable rock. The LA abrasion is an excellent test to quantify that. You want to have 30% maximum for your percent loss of the aggregate gradation after the LA abrasion test. There's a couple of requirements for flat and elongated particles. You have your 3-to-1 requirement and your 5-to-1 requirement, and those are 20% and 5% maximum, respectively. You want to have relatively low water absorption, and that's because you don't want the asphalt or the aggregates to be absorbing all of the asphalt binder. That would add tremendous cost, and it would make you, or you would need to increase your binder content if you were going to do that. So you have a relatively low water absorption percentage. You also have some soundless loss requirements. You can run the soundless loss test for 5 cycles. They have limits for both sodium, the sodium test, and also the magnesium sulfate test. When you run this test, you can either use one or two of either one of those, either the sodium or the magnesium sulfate. If you use the sodium in the soundness test, you have a 15% limit, and then if you use the magnesium sulfate, you have a 20% limit. And then finally, the last coarse aggregate test is the crushed content, and that's the percentage of fractured faces on your coarse aggregate. And because this is relying on that stone-to-stone contact, you want the crushed cubical particles. 100% of the particles are required to have one face crushed, and 90% are required to have 2 or more faces crushed. That's the coarse aggregate. On the other side is that you do want to make sure that your fine aggregate is behaving. You don't want any fine aggregate that would cause problems with the asphalt mastic portion, the asphalt mortar portion. So for the fine aggregate, you also run the cycle, the soundness lost. It's the same specification for the coarse aggregate, but you have your liquid limit and your plasticity index. These are something you generally see actually in soils testing, but because the P200 material, the very fine material that can be quantified through the liquid limit and plasticity index, because that's so important for your SMA mix, they actually incorporate those numbers into the SMA specification to make sure you're getting the property that you need. That's the aggregate properties, and if you can just give me 1 second. For the mineral filler, the mineral filler is defined as either fine mineral matter, and that can be crushed fines, or you can also use something like fly ash. Fly ash is sometimes used in concrete applications because it's cementitious, but because it has such a fine gradation, it can also be used as part of the mastic. The plasticity index for the mineral filler should not be greater than 4. That's going back to the fact that this is a very fine material. It's hard for us in traditional aggregate tests in asphalt to quantify such fine particles, so they use the plasticity index. And then they also have what's called the modified Rigdon voids test as a part of this too. And the modified Rigdon voids must be greater than 50%. And what this test does is you essentially look at the void volume in a dry, compacted mineral filler. So you have a test, and you can actually look it up on YouTube, and there's an example of a Rigdon voids test on YouTube. But what happens is you essentially compact this mineral filler in a dry state, and you can try and quantify the void volume. It's similar in concept to the fine aggregate angularity test, except you're just using P200 material, and instead of letting it fall from the cone into the cup, you use a little tamping bar. You know, there's some little details that are different, but in general, the concept is very same. You're looking at what are the voids in the mineral filler structure. And what this can be done then is it's used to estimate the stiffening effects of the fines when mixed with the asphalt cement. So that mortar or the asphalt mastic is a very important part of stone matrix asphalt. And things like the plasticity index and the Rigdon voids are there in order to help quantify that. The asphalt binder tests are pretty straightforward. You can simply use the standard PG binder grades, and they must meet the requirements of AASHTO M320. For the stabilizing additives, you can use either a cellulose material or a mineral fiber, and these are what are in the M320 AASHTO specification. And you need to use slightly more mineral fiber versus cellulose. It's 0.4% for the mineral fiber, 0.3% for the cellulose, and that's simply because the mineral fibers add surface area, but they do not absorb binder. So you need to add a little more into the mix in order to account for that increase of surface area. And like I mentioned, these stabilizing additives are designed to prevent that drain down. So whether it's sitting in the plant or on a truck or in the field, the asphalt cement will want to drain down because it's such an open mix, and if that happens, then you start losing the mix design that you designed for, especially in the top, and that can lead to premature failure and deterioration. Now, I've alluded to a couple of times the importance of the design gradation, and this is an example. It's from a report out of NCAT by Braham, and he looked into different types of gradations that were used. And you can see here there's one from Germany, one from FHWA, NCHRP, AASHTO, and Unified Facilities. What I really wanted to point out on this slide is, one, that it's extremely gap graded. So the change between the 9.5 millimeter sieve and the 4.75 millimeter sieve, right around where that red circle is, there's a very quick drop-off between sizes. That means that there is a lot of material in that 4.75 to 9.5 millimeter range, or the number 4 to the 3/8 inch sieve range. So that's how you get your gap-graded mix. I also wanted to point out on this slide that the German specification has a relatively higher level passing than number 4. You can see it goes from about 30 to 40, whereas most of the ones in the US are either 20 to 30. Some kind of start going into the 30s. But in general, it's a little bit higher. And there's a very specific reason for that. When the stone matrix asphalt technology came over to the United States, they found that the aggregates were more susceptible to degradation in the US. You were getting higher LA abrasion numbers. And if you start having those higher levels of the breakdown of aggregate, it can make it more difficult to achieve your VMA. So in the US, we found that by producing a slightly coarser mix or having a little less material past the number 4 sieve, you can increase the VMA in that way. So it was kind of an indirect way. By playing with that number 4 sieve, it was an indirect way of helping us achieve the VMA requirements. Moving on from the aggregate properties more to the volumetric properties, you can see here the air void design is 4%, just like any standard asphalt concrete mix design, but that's the maximum, and there's actually some allocation to even go lower than that, which we'll talk about in some upcoming slides. Your VMA is a 17% minimum. You have what's called a VCA, which I'll go over in upcoming slides, and the VCA needs to be less than the VCA DRC. You have your VCA mix and your VCA DRC. I'll go over those two terms in a couple of in the upcoming slides, so we can understand the VCA. The TSR, the tensile strength ratio, needs to be less than 0.8. You have your drain down test. There's actually an ASHTO drain down test that's run, and you want a 0.3% max drain down, which is, you can roughly relate that to, you want no more than 0.3% of the binder actually moving down in your mixture. And then finally, your asphalt binder content, you're looking for 6%. So there's kind of a lot of information on here. I think air voids, VMA, TSR, those are pretty straightforward. But there are some special considerations for air voids. I want to talk a little bit more about this VCA, both from the mix and the DRC. I'll define those in upcoming slides. And then also talk a little bit more about the binder content. So first, starting out with, for the air voids, you can actually have a range for between 3 and 4% on low volume roads or cold climates. So as the volume goes down, as the climate gets cooler, you can actually start dropping those air voids. And also, if your aggregate gravity, so the specific gravity of the aggregate you're using, if that's above 2.75, you may also want to lower your asphalt content. And that has to do with some of the mix proportioning and such. So the air voids can actually change, and also the asphalt content as well, depending on your volumes, your climates, and then also the aggregates that you're using. Now, so those were the asphalt content and the air voids. I mentioned on the previous slide that we would go over a couple more things. But for the VCA, which stands for voids in coarse aggregate, it's a little more complicated. So I'm going to spend a little bit more time talking about that. Before we go on, I know students in the class love pictures. So here's a picture from Oregon State. You can see a traditional dense SMA asphalt sample on the left, and then the SMA is on the right. And you can really very clearly see those larger size aggregates on the right in the SMA mix, and how that mix is much more open than the dense HMA. So the voids in coarse aggregate. So if you recall, we had a VCA mix and a VCA DRC. So for the best performance, the reason this came about is the SMA must have coarse aggregates skeleton with stone-to-stone content. So you can imagine how it's very important to understand the voids in coarse aggregate in order to get that stone-on-stone content. Coarse aggregate in SMA is defined as anything retained on a number 4 sieve if you have a 1/2 inch nominal maximum aggregate size. Coarse aggregate is defined as anything retained on the number 8 sieve for a 3/8 inch nominal maximum size HMA. So you can see that coarse aggregate, the definition of, actually changes a little bit depending on what the nominal maximum aggregate size is of your mixture. So the stone-on-stone contact is, and I believe I'm missing a word there. Oh no, I'm not. I apologize. The stone-on-stone contact occurs when the VCA of the compacted mix, which is VCA mix, is less than the VCA of the dry rotted test, which is the VCA DRC. So when you're going through the design process, you need to run a dry rotted test on the coarse aggregate. And that's not something that's traditionally run on aggregates for asphalt concrete. It is for Portland cement concrete, but not for asphalt concrete. But by running the dry rotted test, you get a very good idea of the stone-to-stone contact of the aggregate structure that you're evaluating. So in order to achieve that stone-on-stone contact, you want the VCA of the mix being less than the VCA of the dry rotted test. And this is how you calculate the VCA of the mix and the VCA of the dry rotted test. The VCA of the mix is simply 100 minus the ratio of the bulk specific gravity of the compacted mixture, or the GMB, divided by the bulk specific gravity of the coarse aggregate, and you need to multiply that by the percent of coarse aggregate in the total mixture. The VCA for the DRC, or the dry rotted test, is the bulk specific gravity of the coarse aggregate times the unit weight of the coarse aggregate, and you subtract from that value the unit weight of water, and you divide it by the bulk specific gravity of the aggregate times the unit weight of the coarse aggregate fraction. So by running the bulk specific gravity test that you need to do, by determining your percentage of coarse aggregate, and by determining your unit weight of the coarse aggregate in the dry rotted condition, you can calculate the VCA of the mix and the VCA of the dry rotted condition. And if you recall, for SMA, for stone matrix asphalt, you want the VCA of the mix to be less than the VCA of the dry rotted condition. Alright, so we went through a whole bunch of things there in design. If you guys have any questions, please raise your electronic hand, and we can go from there. Well, there are no questions, so we'll be moving on. For the production of the SMA, just the aggregates, you generally need to have fractionated aggregates. And this is where you actually pre-sort your aggregates into specific sizes. So generally we have our stockpiles divided into different top-sized rocks throughout a plant. But for SMA, if you really want to control your gradation, it's recommended that you actually fractionate your aggregate. So you take those stockpiles and then break them down into the smaller sizes. And this allows for a more precise control of gradation. Now, I fully understand that this is an extremely large process to do, especially in a plant. It's relatively easy to do in a laboratory. Us researchers love doing stuff like that. We love our precision. But for the best performance in the plant or in the field, it's recommended that it's actually done in the plant as well. So one way to simplify this is often a single stockpile is used. Because this is such a gap-graded mix, you can just choose the one rock that you're focusing on and use a single stockpile. Something that can help is if you split this stockpile into two cold feed bins. Generally, when you're loading one type of aggregate into a cold feed bin, one type of aggregate for one cold feed bin. But with SMA, since you're generally only using one type of aggregate and you have the single stockpile, and you may actually have it broken down into the fractionated aggregate, it's recommended that you actually use two cold feed bins. And one way you can do this in the plant is by using portable screening equipment. For the mineral filler addition, there's a couple different ways you can go about this. You can simply insert it into the mixing chamber or in a cold feed bin on a drum plant. Both of those are acceptable. If you're using a batch plant, you can insert it directly into the pug mill. And the reason that you want to kind of take special care of this is because a lot of plants now have baghouse fine removers. So they literally have these vacuums in the plants that suck out the fines that are just in suspension within the drums. And if you put the mineral filler in too soon, one of the problems you can have is that mineral filler can kick right back up and it'll get sucked out into the baghouse fine. So you're kind of losing the value of this mineral filler. Another reason that you want to be a little bit careful is that it does need to be added dry. You want no moisture in your mineral fillers. Because it's dry, that means it'll kick up more, but you also want to make sure that it's able to flow over the other aggregate and mix nicely with the asphalt cement. So you want absolutely no moisture in there. That's for the mineral fillers and the aggregates. Now for the cellulose fibers, these are the fibers that help prevent drain down. They can be added in two ways if you're using a batch plant. A lot of times these fibers come in like 50-pound or maybe 30-pound bags. You can simply toss one of those bags into a pug mill. The pug mill will rip it apart and mix it all up. And if you mix it dry with the aggregate for about 6 to 10 seconds, they'll be pretty evenly distributed in your aggregate. You can add the binder and then mix it all together. Now if you're using a drum plant, you can add it through a feeder system, and that allows you to vary your feed rate with whatever plant production rate you're using. So if this is a new material that your plant hasn't used before, you might go a little more slowly at the beginning until you get the hang of it. Once everything's working okay, you can ramp up production. By using a feeder system for the drum plant, then you can just bump that up too as well for the fibers. That's on the production side. Now over on to the construction side. It's highly, highly recommended to use a material transfer vehicle or an MTV. Now these are often found on asphalt concrete job sites. What they are is they're basically a small little pug mill. They can have heating units if you want to get the temperature back up. But what it allows you to do is it allows you to take mix that's maybe been sitting in a truck for a little while. It may have some segregation, either thermal or aggregate. It allows it to remix it. So by taking this material, putting it in a material transfer vehicle, and remixing it, you can decrease the aggregate segregation, and you can reduce thermal segregation and any sort of crushing that you may have. With more consistent aggregate gradation, with less segregation, and with less thermal segregation, you can improve your in-place density. And moving right into the in-place density, the reason a screed paver, on I think the second or third slide I mentioned that the screed paver needs a heavy tamping bar, is that you want a very high, that should be degree, not decree, I apologize about that. You should have a very high degree of initial compaction directly behind the paver. And that's because SMA is very open, and because it's a surface course, sometimes it can be on the thinner side as well. And if you have a very open, relatively thin mix, a lot of air can get in there and your mix cools down very quickly. And as your mix cools down, you'll have a harder time getting the compaction you need. So by having a heavy tamping bar on that screed paver, you're getting that initial compaction almost immediately after the material gets put out by the paver, and you're able to get that quick initial compaction. And that will not only help your smoothness, but it can also minimize what's called differential roll down, which is a change in thickness between the paver and your final compaction. And with SMA, you really want to have that compacted as quickly as possible because it's so open, it can start cooling, and you won't be able to get the compaction that you need. Something that I read about in a couple of the articles as well is that people are surprised at how the paving train is quite a bit shorter than traditional HMA. So if you're on a traditional HMA job, you'll have your dump trucks come in with the mix. You might have a material transfer vehicle. You'll have your paver. Then a little while back, you'll have your pneumatic rollers, and you might have vibratory rollers and a steel wheel roller to finish. You have this very long paving train. But with SMA, you want to get that material down, and you want it to immediately be compacted, and you don't want to wait a whole long time for that. So your paving train is quite short compared to traditional HMA jobs. And this is just a picture of the tamping bars. This is the underneath portion of a paver. The material is coming from your left, and it'll be laid down, and those tamping bars will apply an initial compaction right after it comes out of the paver. And we've been talking quite a bit about compaction here, and there's good reason for that. Like I said, you want to get it compacted as quickly as possible because of the open nature of the mix. Air can get into the mix, it can start cooling quickly, and if you don't get that compaction down, then you won't get the densities that you have designed for. They recommend not using a vibratory compactor. That's for a couple of reasons. One, you can actually bring the excess binder to the surface. We were talking about drain down. We don't want asphalt to go down. We also don't want asphalt to go up. And by using a vibratory compaction, that's been shown to actually start to bring the binder to the surface. You're also more likely to fracture your coarse aggregate because you're relying so heavily on the stone-to-stone contact. Putting a vibratory compactor on there could actually fracture the aggregate. It's all these coarse aggregates just pounding against each other. Now, they do sometimes put a vibratory compactor on a little later in the compaction process, but they definitely recommend leading with a static roller. And then if you feel you need that vibratory compaction, you can do subsequent compaction on a low amplitude, high frequency basis. I was reading in some of the specifications and some of the articles about how there are kind of special terms associated with the construction of the SMA. And one of those is the pounds per linear inch, or PLI. And the PLI for, I think, normal compactors is around 200, maybe 150. But for SMA, that pounds per linear inch goes up to 300. So you want a very strong, very high compaction. And something that they found is that can really only be accomplished with narrow rollers. So some of these wider rollers that are out, they do very well on hot mix jobs, but they can't get up to that 300 PLI limit. But the more narrow rollers with the high compaction efforts can actually achieve that 300 PLI. And then finally, rubber tire rollers are not recommended because there is a chance for pickup. Because this is such an open mix, you have that stone-to-stone contact, those rubber tire rollers can actually grip on to the coarse aggregate and bring them up as they roll over. And that's called the pickup. And you obviously don't want to have your pavement surface coming up on your rollers. It's kind of a 0 for 2. Not only are you not getting your density, but then you're also picking up what you just put down. And then finally, for the construction of the SMA for your final product, these are kind of some of the things that you'll be looking for. The in-place density is absolutely critical. You need to have less than 6% after your rollers go over. If you don't have that, chances are you won't be able to get down to your 4% or even less percent with the traffic. Your lift thicknesses are relatively narrow. They're 1 to 2 inches. And they recommend that that can be based on your nominal maximum aggregate size. And you want to have a thickness to nominal maximum aggregate size ratio of 4 to 1. So for example, if you have a 1/2 inch nominal maximum aggregate size, in order to get a 4 to 1 ratio, you need to multiply that 1/2 times 4, and you get 2 inches. So you'd have 2 inches of SMA. One of the things that they had found is that sometimes early skid resistance on SMA projects can be a problem, and that's because you have this high film thickness on the coarse aggregate. The stone-to-stone contact, they're held together by this relatively high binder content, which means you have a lot of binder on your coarse aggregate. And that coarse aggregate that's right on top of that pavement surface layer, you're going to have quite a bit of binder staying on top of there. So some people have recommended adding a little bit of sand, sprinkling that sand on the surface after all your rollers are done. And what that does is that kind of neutralizes that binder that's on the very top. And you want to make sure you do that when the pavement's still a little warm, so the sand can actually get into that top binder. Now the sand will absorb a little bit of excess binder, and it will reduce permeability a little bit. If you have a very open mix and you're dropping sand in there, obviously some of the sand will go down into your hole, into the voids. But that sand that's in the binder on the top, that will eventually be worn away. So you don't need to worry about the skid resistance long term with that sand in there because it'll all be worn away. The sand is simply used to help with initial skid resistance. So that's a little bit about production and construction. Like I said, I'm going to go over 3 field examples, but if there are any questions at this time, I'd encourage you to raise your hand. Yes, and we have Ms. Shaw raising her hand, so I'll wait for her to type the question in. Thank you. So the question is weather a consideration? For example, high humidity, low humidity, temperatures, all of that. I did not read anything about humidity in particular, and actually I didn't read anything individually about weather as well. I think a lot of the projects I read about were kind of under ideal conditions. It's a new product. You don't want to go out in unideal conditions. I would assume that it's a little more difficult to lay this as the temperature decreases because, again, thinking about this compaction, with the high air voids, a lot of air will move through here quickly. So I would caution against too low of temperatures, but I think that this is something that I didn't see a whole lot on, and I would encourage you, if you have further questions about the weather. I briefly went through 3 reports that I will go over 1 slide each. I mean, they do not do the reports justice, but I'll also provide links to those reports, and they may go a little more in depth into weather on those. But as far as I could read, weather is not a big consideration. Are there any other questions at this time? Okay, we got a question from Mr. Bernier. I'll be typing it in. So the question is, the SuperPave dense graded mixtures recommend a 3:1 minimum thickness with nominal maximum aggregate size, whereas SMA requires 4:1 thickness to nominal maximum aggregate size ratios. And the question is, why is there a difference between that 4:1 and 3:1? 4:1 for the SMA, 3:1 for the dense graded. Off the top of my head, I'm not 100% sure. I would think, though, it has to do with the fact that because you are depending so much on that stone-to-stone contact, you want to make sure that you're really getting strong stone-to-stone contact. And if you only have 3 coarse aggregates stacked up, there is a possibility if there's something wrong with one of those, then you've lost 33% of your structure. Whereas if you have 4% coarse aggregates stacked up, and one of those, there's a problem with that, then it's possible that you might not have as many long-term problems with that. So kind of being a little more conservative with your pavement thickness, recognizing that the coarse aggregates are much more critical, that would be my guess. So thank you for that question. The next question is from Jay, and he asks, are there any changes to the mix design when SMA is produced using warm mix technology? Now that's an excellent question, and if I pull out my AASHTO standards, which I'm actually literally doing right now, they were both put out in 2008, these 2 AASHTO SMA standards, and they have no wordage in here about warm mix asphalt. And it's a very interesting question because I know that even traditional hot mix asphalt, the AASHTO standard is now just starting to be addressed using warm mix technology and also wrap and shingle, some other things. But I think that these standards and designing and actual design guidelines, there's quite a bit of lag time between technology and these products. Because SMA is relatively new, it's only been around about 20 years in the US, and because warm mix is also relatively new, I haven't seen any research done or any work done in trying to incorporate warm mix technology. That actually sounds like a very good research needs statement for example, Transportation Research Board, where they actually call for new research ideas, because I think not only warm mix in general, but You know, how does foaming technologies change with that? How do chemical technologies change? I think that's just an excellent question about warm mix and SMA, and I just don't think we've gotten there yet. Okay, good. Well, thank you for those questions. I believe that's it. So I'll go over now some field examples really briefly. These are the 3 reports that I reviewed, and I will cut and paste the links here into the chat box. So this first link is from Illinois, and if you click on that link, you can actually download the PDF file, and that is entitled Evaluation of Stone Matrix Asphalt. The next one we'll be looking at is from Wisconsin, and that is very aptly titled Stone Matrix Asphalt, the Wisconsin Experience. And then I also chose the Virginia report because the Virginia report went into a little bit of cost analysis. And I know that cost is always on the forefront of people's minds, so we'll go over a little bit about Virginia's experience with cost. But these are 3 very good reports. And for example, Judith Shaw, she asked a question regarding to environment. If you're interested in like specific questions like that, I would think that these reports may have some wordage on that. They're between 75 and 150 pages long, so I haven't read them all, but when you're looking for something specific, you may be able to find some pretty detailed answers in there. So to start out with Illinois, this report was written in 1996, so this was done almost immediately after the technology was introduced to the U.S. from Europe. And from a cost perspective, the SMA was 41% higher in cost than traditional dense graded HMA, but they believe that the cost could be slightly reduced through competitive bidding. And I also just want to remind you that this is a 16-year-old report, and prices have changed significantly in the past 16 years, but it is a number, and SMA is generally a little bit more expensive than traditional dense graded mix. The Illinois group found that the SMA mixtures strongly adhered to both production and construction equipment. So this is going back to what I was saying with the pneumatic tire roller. You don't want to use pneumatic tire rollers because of pickup. In general, SMA is pretty sticky, and so it will adhere to both your production and construction equipment, so you do need to be careful with that. In Illinois, they successfully used both batch and drum plants. They found that for the mix and laydown temperatures, I apologize, there was a little bit about weather, but if the mix and laydown temperatures are too hot, you're going to have more drain down. That makes sense. As asphalt cement temperature increases, there is a higher chance for that mix, or for the asphalt cement to drain down a little bit. But then if it's too cool, it's difficult to compact. They found that vibratory rollers broke down aggregate, and also they found some problems with that skid resistance and that surface friction in early life, and they used some sand blotting for that. So this is, like I said, I think this is like a 150-page report or something. These are just the real big highlights, but it showed that Illinois did have some success. They had some problems, but they were able to overcome those problems, and overall they were pretty neutral about this technology. They didn't go all out. They didn't love it, but they didn't find anything terribly bad about it either. So moving on to Wisconsin, this is about 6 years later. They found from a cracking perspective after, so what they did is in 2002 they wrote this report, but all of these mixtures were placed down in the late 90s. So all of this data is after about 5 years of in-place service. So after 5 years, they found they had approximately 30 to 40% less cracking than standard dense graded HMA. And they found that there was even less cracking, so there's a lower amounts of cracking when you had higher abrasion aggregate values. Because they found that the larger aggregates, the larger, stronger, more durable aggregates helped impede that cracking. They did not find a significant difference between the rutting of SMA and traditional HMA. That goes a little bit against what a lot of other sources say. maybe Wisconsin just builds really rut-resistant HMA, traditional dense graded roads. I'm not sure about that. They found that the riding quality on SMA was generally a little rougher. But they did want to make the caveat to that statement by they measured the roughness of the road by using digital equipment, by using those laser scanners. And the laser scanners may have read the open texture of HMA as roughness. So these laser scanners, when they're scanning the road, they're meant to quantify cracking, rutting, potholes, any sort of surface defects. And so when you're shooting that laser down an air void, and because SMA has very high air voids, especially up to the surface, those air voids may have been read as rougher. They found that after 5 years they had less friction, but overall they found that the SMA performed better than the standard HMA pavements over the 5-year study. And the last one we'll go over, and I wanted to throw this in here because they have quite a bit more numbers, and it's from 2007. That's almost 6 years ago now, but it's a little newer than the other two, so that the costs are, I think, a little closer to what we have today. And they found that overall, from a performance standpoint, the SMA outperformed the dense graded HMA when placed in similar condition. And they felt that this performance offset the higher initial cost. And they found that the SMA cost about 32% higher. They found that SMA was the most cost-effective material, the most cost-effective HMA material for use in maintaining pavements on interstates. And they recommended that VDOT, the Virginia DOT, could be able to fund their interstate resurfacing program by using SMA because it's more robust. And you can see here in the table below, they have 3 different mixtures. They have a standard mix 9.5, a standard mix 12.5, and then the SMA 12.5. You can see the price differences. The SMA is quite a bit more expensive, but it has that longer life. And then they kind of went through the net present costs, how much they could resurface and the resurfacing costs and such, those things. So they did find out that with that longer life, the traditional hot mix had around 8 years, 7.5 to 8.5 years. The SMA they predicted to have 14 years. With that extended life, they would be able to offset the cost. So those are 3 state reports that were posted, and I really appreciate if anyone is online from those 3 states. I just would like to say thank you for posting all those reports, because there is a tremendous amount of information in those reports. They're not only great for these webinars, but they're also great for classes, so I really appreciate that. A couple more electronic resources that can be found online, and most of the front matter to this presentation were from these 2 electronic resources. The National Cooperative Highway Research Program and CHRP put together the Designing Stone Matrix Asphalt Mixtures for Rut-Resistant Pavements. There's a URL for that. And then I mentioned Auburn University put together a very nice report for actually airfield pavements, but they had a very good amount of front matter on what SMA is in general, and you can find that in that next link. So those are just some links if you're interested in finding out a little bit more. So in summary, before I lose everyone here, I will take questions at the very end, but I want to go through these logistics. I don't want to keep people on for more than the hour scheduled time. We have the spring schedule set up here. So next spring, Tuesday, February 5th, we'll be talking about different methods of asphalt pavement crack repair, and that was requested by industry. On Tuesday, March 5th, we'll talk a little bit about pavement management systems, requested by the Virginia DOT. I got 3 requests, so I had to find the 4th one. A big part of my job and what I research is sustainability, so you guys will get to learn a little bit about sustainability in pavements on April 2nd. And then on May 7th, industry requested something on foamed asphalt and laboratory testing, specifically the M sub R value, the resilient modulus. So we'll go over those next semester. My life is on spring and fall semesters, so next spring we'll go over those. And all Pavinars begin at 12 noon Central Time. As I mentioned, your PDH hours will be emailed to you no later than this Friday. You can rewatch the Pavinars after I post them through the website. Also through the website you can submit topics, so please submit those. It was very helpful for me to hear the topics that you're interested in, and it's fun to look into things that I might not normally look into. And the next Pavinar will be Tuesday, February 5th at noon, and it'll be on different methods of asphalt pavement crack repair. So with that, I'll open the floor to questions, and I'll stick around for as long as you guys need until the questions are done. But I appreciate you joining me today and hope you guys all have a great holiday season. So thank you, Danny, for your question. If you could type the question into the chat box, we'll go from there. So Danny is asking about the sand application to reduce skid resistance. And he said that the pavement, or adding that sand, could reduce permeability, and will the gradual filling of voids on the long-term function of the pavement? Yes, so that's a very good point. If what Danny's talking about is if you sand pavement on a regular basis, like during the winter, if you put de-icing down, those type of things, or in general any material, deleterious material, how would that influence the openness of the pavement? If the SMA has been put down in order to help the drainage, you will want to try and keep the SMA clear. And I didn't read anything, but I know on other open mixtures you can actually use like high pressure water to clean out open graded mixtures in order to maintain those voids. But I think that the beauty of SMA is if material does fill into there, it doesn't necessarily compromise the material itself, the filling, but the side effects could. So if you start like getting perhaps clay in there, and if you get clay in your mix and then it rains, that clay might want to expand, and expanding material within your SMA could cause problems. So I think that keeping those voids clear is important. And I apologize, I didn't look over that at all, but I'm sure there are technologies out there where you can actually keep those voids clear. And that would probably be an added cost that if you're looking into doing it, you would definitely need to account for in your maintenance strategies. So thank you for that question. Are there any other questions? Okay, we have another question from Jay, and he said, would it be easier to control the drain down if a polymer modified asphalt is used? And I think actually that would be an interesting question, because polymers would act in a way as like a fibrous material, kind of holding that up. And I would think that polymer modified asphalt is less susceptible to drain down. And I think you know, by running the drain down test, you could actually verify that in the lab. So run the AASHTO drain down tests on both unmodified and modified binder, and then see what those differences are. And if you get the proper performance that you need, you might not need to add those additional fibers. Are there any other questions? All right, well, it's 1 o'clock, so I thank you all for joining me. If you have any lingering questions, feel free to raise your hand and I'll stick around. But again, thank you all very much and hope you have a great holiday season. We'll see you in February.